Okay. I'd like to start by thanking the organizers, Sam and Supurna, for inviting me here and giving me this opportunity to give this talk. And since this is the third review talk on topological phases of quantum matter, there's bound to be some repetition of some of the things which were said earlier. I think I have some amount of overlap with Vijay Shenoy's talk, essentially because both of us have been talking about, he was also talking and I will also be talking about short-range entangled phases or symmetry protected phases, but I think you were talking more about interacting systems. So with that caveat, let me start. I'll start again by mentioning that the 2016 Nobel Prize in Physics was awarded to Thoulist, Haldane, and Kosterlitz for theoretical discoveries of topological phase transition and topological phases of matter. But although this was the first to mention topological phases, this is not actually really the first Nobel Prize for topological phases. The first was in 1982 to Klaus von Klitzing for discovery of the quantized Hall effect. And now we know that this is actually the first topological phase. The second was given in 1998 to Laughlin, Sturmer, and Su for the discovery of a new form of quantum fluid with fractionally charged excitations. In fact, this is again one of those interacting topological phases. And one can probably expect many more in the future, as Vijay already said. Because if you look at one of the recent preprints about a year and a half ago, what they showed is that roughly 24% of the materials in the world are topological. And roughly half of them are topological insulators. So one can expect, these were not things that were known before, so one can expect that there will be many new phenomena and probably many more Nobel Prizes for topological materials. So the plan of my talk is as follows. I'll give a brief introduction and then discuss the quantum Hall effect in some detail because that's the first topological phase. I'll talk about also the edge states and the recognition of the bulk boundary correspondence. And then I'll talk about topological insulators and topological superconductors and end with just some generalizations. So yeah, again, I'm starting assuming that the students in the audience at a simple level, and start as Vijay also started out with, what are phases of matter? We are all familiar with phases such as gas, liquid, and solid. If you reduce the temperature of water, it freezes, becomes a solid. If you increase temperature of water, it boils, turns into a vapor. So what one means by a phase is actually not just e raised to I theta, but here a collection of particles with some properties that distinguish it from other phases. And earlier, as again was discussed earlier, phases were just classified in terms of Landau theory, in terms of symmetries. So ferromagnets break the rotational symmetry. Liquid solid, it breaks the translational positional symmetry. This ferromagnets break the rotational symmetry in the spin space, etc. But in the last 10-15 years, there's been a paradigm shift in the way of classifying phases, which is now based on topology, or more correctly, as was mentioned in the last talk, on the interplay of topology and symmetry. And before I start with these phases, why are these interesting? You could say that new phases of matter are always exciting. And one of the other interesting things is many of these topological phases, including even the non-interacting ones, have excitations which can obey unusual statistics. So they can be anyonic and also non-abelian. One can have non-abelian statistics. And these kinds of excitations, the Majorana modes, etc., are expected to be relevant in making quantum computers. So which is one reason there's been a lot of, in the condensed matter community at least, there's a lot of interest in topological materials. And people have been trying to look for ways to look for these Majorana modes. There are also other unusual excitations which are earlier, which were only considered in the high energy community, such as monopoles, dyons, axions, etc. And these, it looked like it looks like these kinds of excitations can be found in low energy material sciences. So this is another reason that people have been interested in these materials. Again, a very brief introduction of what is topology. It's a branch of mathematics dealing with shapes. And topological implies something which is not changed by small perturbations and depends on the system as a whole. For instance, if you look at the first line, all one cares about is whether this point Z0 is enclosed and how many times, whether it's enclosed once, whether it's enclosed in this way or in this way. These two will both have the same topological quantum number. If it's not enclosed, it will have a different topological number. If it's enclosed twice, it will have a different topological number, and so on. So more technically, the mappings from one space, for example, 2D space with one point removed, to the space of wave functions are classified by a topological invariant, which is the winding number. And similarly, all these other kinds of mappings are also classified by a number, which can be the Chern number, etc. We'll come to that later. And for a quantum condensed matter system, the space that we are normally talking about is momentum space. And it is something which is a Brillouin zone, which often has periodic boundary conditions. In 1D, it will be a circle. In 2D, it can be a torus, and so on. And the topological classification that one talks of is the mappings of this Brillouin zone to the space of gapped single particle Hamiltonians, as Vijay was talking about, because wave functions for every band define a map from the Brillouin zone to the space of physical states. So what are topological phases now? They have some property to which an integer can be assigned, which depends only on the global properties and cannot be destroyed by impurities or disorder. For example, conductance in the quantum Hall effect. And to change the topological phase, one needs to do something drastic in the sense of make a hole in the surface or something. In real physical systems, the idea is that as long as the system has a mass gap, physical states can be changed slightly and it will not make any difference. The topological invariant will not change. This is what is called topological protection. But when the system becomes massless or gapless, then even small changes can make a major difference, and then the topological invariant is no longer protected. Okay? So with this introduction, let me come to the first topological phase, which was discovered 35 years ago, which is the integer quantum Hall effect. Again, assuming not everyone, most of you I know are familiar with the Hall effect and quantum Hall effect, but since it's also a general talk for students, let me just mention. What you have is in the conventional Hall effect is that you have a piece of metal over here, and then you can think of it as you have a magnetic field which is perpendicular to it, and then you apply an electric field in one direction, and because of the Lorentz force, what you find is that the electrons get, there's a force which acts on the electrons, and because of that electric force on the electrons, it induces a charge buildup. So if you calculate, you can actually just do the math and calculate what is exactly the perpendicular Hall voltage because of the fact that you have an electric current in this direction and a magnetic field perpendicular to it. If you calculate that, what you find is that the Hall voltage is actually Hall voltage, or what is called the resistance in the perpendicular direction rho xy. Hall voltage is Ix by n dq. N is the number of electrons, d is this thickness over here, and q is the charge of the electron. And in fact, this is what is normally was used earlier to find out whether it's electrons or holes which are carrying the charge, for instance, in semiconductors. Because the sign of the Hall voltage was what tells you the sign of this charge. And what you can see from this is that the Hall voltage and the Hall resistance is actually directly proportional to the magnetic field. So the larger is the magnetic field, the more you would expect the Hall voltage to be. So, but what happened was that in 1982, when von Klitzek did the experiment in a two-dimensional electron system at low temperatures and in the presence of strong magnetic fields, what he found is that there was the Hall conductance, instead of being a straight line as expected, was quantized in terms of integers. What they found when they did actually the measurement was that as a function of the magnetic field, the transverse resistance was quantized in steps. The longitudinal resistance went to 0 precisely at the points where the perpendicular resistance was quantized. And they found that the Hall conductance was quantized in units of E squared over H. And they found that the conductance was extremely accurate. In fact, the unit of resistance is now called the von Klitzek and is given by this number with the accuracy up to this level of decimal place. It's now the standard of resistance. And this is actually very unusual because the measurement is being done in it can be done in any material, and it is not at a fixed temperature, not at a fixed length, nothing, but you get the same answer every time. So this is usually these kinds of units of stuff are done by having in particle physics. But here you're finding it in a complicated many-body system. So to understand this, what one needs to do, use quantum mechanics, because classically, clearly, semi-classically, this was expected to be a straight line. As I think Bhaskaran already also discussed slightly, the actual problem that one needs to understand the integer quantum Hall effect is just a quantum mechanical problem of an electron moving in 2 dimensions in a magnetic field in the z direction. And you can solve this problem explicitly and find that the solutions are highly degenerate Landau levels. So what you might think is when you put electrons in Landau levels, I think there are gaps in the spectrum. So when you put your Fermi level in the gap, you might think you should get an insulator, but it is not. As we already know also, the electrons drift when we apply a magnetic field, and one gets a Hall current which is perpendicular to the electric field. So what happens is that when the real picture, when you try to work it out, what you find is that this is the Hall current picture, and here I've plotted the density of states as a function of the electrons. And these, for a clean system, would just be these single lines, right? Because they degenerate, and the degeneracy is something which you can compute. But once you have disorder in the picture, then what you find is that these degenerate states you separate into localized and delocalized states, and at the center of these points where the conductance changes from one to the other, you have delocalized states, whereas when the density of levels goes through where there are only localized states, then you get exactly plateaus. So when the density of electrons is such that there are full Landau levels, that's precisely when you get these plateaus in the system. So what you understand is that whenever there is a full Landau level, you can think of it as being unusually stable, and at those levels is when you're getting the plateaus in the system. And you can see how the current changes by having a picture of localized and delocalized levels, and as you go through it, you can see when you'll get into a plateau and when you'll get into extended levels. So it's only the states near the center of the band which carry current and which is quantized. As I said already, the remarkable fact is that the quantization is so extraordinarily accurate. Sigma xy is equal to n e squared by h, with n is equal to integer, and the measured accuracy is 1 part in a billion. This is a measurement which is made in a complex macroscopic many-body state with impurities at different temperatures, different size, shape materials, etc. So the question can be, how does this happen? Why does this happen? And this is the answer that Thouless, etc. gave. They recognize that the Hall current is related to a topological quantum number like the winding number. And since the wave functions for each Landau band define a map from the Brillouin zone, which is, because it's a two-dimensional system, you have kx and ky, so it forms a two torus. You can have wave functions which are which map from this to the space of physical states, and you can compute a number which is called the Chern number or the TKNN number. So the phase of this wave function winds as we move around the Brillouin zone, and this winding is captured by the magnetic potential AIK, which is minus I UK dk I UK, where UK are the block wave functions. And when we integrate the magnetic flux of this, the magnetic field due to this potential, then you get something which is called the Chern number. And this Chern number is what is topologically protected, because the conductance is actually related to the sum over alpha of C alpha, where C alpha is the Chern number and the sum is over all the filled bands. So this is what explains the extraordinary accuracy of the conductance quantization, because it relates to an integer which does not change in the presence of impurities. It depends only on the number of filled Landau levels. So even though you have impurities in the system and you have localized and delocalized states, what matters is only this fact that each of these bands gives rise to a Chern number. So what is the consequence of the fact that you have a Chern number for each of these, for each band? You can also show that because of there is a bulk boundary correspondence, in the sense that you can either consider the Chern number of the band, or you can count the number of edge states which are at the edge of the sample. So you can try to understand what happens at the boundary between different topological states. You can give a semi-classical argument that if you have a magnetic field and if you have a sample and you have magnetic field perpendicular to it, then the electrons go around in Landau orbits, but at the edges of the sample they can't complete the orbits if the sample has an edge. So a semi-classical picture implies that at the edges you have to have what are called skipping orbits. And this basically, you can see that since it goes only in one direction, at the two edges the skipping orbits mean only one-way motion, because you have to go like this. At this edge you go like this, but there's nothing which can come back. So at this edge the electrons have to move in this direction. At this edge, they have to move in this direction. So transport actually happens only at the edges. In fact, there's another way of understanding this, that even if you have impurities in the center of the sample, they will all get trapped or localized due to the valleys and the hills that occur due to disorder. And it's only at the edges of the sample that you can have this kind of motion. In the quantum mechanical language, one can see that the edge states have to be actually chiral Dirac fermions at both the top and the bottom edges, because if you solve the problem in real space, what you find is at the two edges of the sample, if it's at y is equal to 0 and y is equal to L, you can see that the Landau levels actually bend at the edges, and the bending, the velocity at this edge and this edge is opposite and is given by 1 over EB dE by dy. So what you can see is that, for instance, if I had 3 filled Landau levels, if my Fermi level was at this point, then at the edge I would get each of the edges, at the top edge and the bottom edge, I would get 3 edge states. Because in the rest of the sample, there is nothing, in the bulk of the sample, there are no states available, but the states that are available are only at the 2 edges. And these 2 edges, the electrons move in opposite direction because of this velocity which is opposite in the 2 opposite directions. And this, if you draw it in momentum space, is exactly what you would get over here. You will get one of these chiral edge states. So the bulk boundary correspondence is that the Chern number in the bulk is related to the number of edge states that you have at the edge of the sample. And this is again related to index theorems in mathematics. As I said earlier, the direction and flow, or the direction of flow at both the edges is unidirectional. It's fixed by the sign of the magnetic field, and only the edge states carry current. And because of the spatial separation of the right movers go in this direction, left movers go in this direction, even if there is an impurity, there is no channel for it to get backscattered. And so you can think of this purely as continuing here. And this is another way, again, a hand-waving way of explaining why you do not get backscattering in these kinds of things. Also, one can argue that when the system evolves from one integer quantum Hall state to another, the number of edge states has to change. And this cannot happen if the bulk remains insulating, else the invariant cannot change. So if you want the to go from one integer quantum Hall state to another integer quantum Hall state, you are forced to have current go through the bulk, which means that there has to be states states in the bulk close to the Fermi level, and then you can change the number of edge states. If there is nothing which goes through the bulk, you cannot change the number of edge states. So the bulk gap has to close, implies current through the bulk when the Chern invariant changes. So main points of a topological phase is that the bulk is an insulator and the current is only carried by the edge states. And second, there is quantized transport because there is no backscattering. The quantum Hall effect was initially seen to occur in a 2-dimensional electron gas formed in a layer of aluminum gallium arsenide sandwiched between gallium arsenide material. But in recent times, the quantum Hall effect has been seen in other 2D materials like graphene as well. But all of this topological transport in the integer quantum Hall effect happens at very low temperatures and very high magnetic fields. And it is the recognition that topological phases can exist in bands even without the need for magnetic fields, which has led to this new revolution of topological materials in the last decade. So this is topological materials post 2005. And they realized that strong magnetic fields were not required. And this is one case, the quantum Hall effect was experimentally found, and then people came up with the theory for it. But here, actually, the prediction came first. They predicted the insulating materials with metallic surface states without magnetic field or time reversal breaking. By the entire group of people which came up in different ways, but the prediction came before the actual experiment was seen. What they realized is that materials with a strong spin-orbit coupling can behave like a quantum Hall state. And what is the material is actually insulating in the bulk, but with conducting states. And at a very hand-waving level, it's as if like it's a block of wood covered with a metal, except that it's a single material. And this was a joke that is in one of Shankar's papers, that don't stand on a topological insulator to change a light bulb, because it's metallic on the edges, right, surface. And you might, if 1/4 of the materials in the world are topological, you might wonder why it was not discovered earlier. One reason was probably that it included a need for sophisticated instruments that can map local density of states, because you need to know which states in the sample are actually carrying the current. If you just look at the overall current, you wouldn't know that. And also the theoretical, What? I think they have RPACE experiments, angle resort photoemission spectroscopy. Yeah, you'll show some of the slides, I say. I just have a picture of this thing. So that tells you which are the current carrying states in the system. Theoretically also, what happened was that earlier one knew the dispersion of the materials, but you needed understanding of the Berry phases and structures of the mappings of the Brillouin zone to the Hamiltonian, which is more sophisticated than just knowing the spectrum. So, which is perhaps the reason that it took so long to discover them. And as I already mentioned, they were predicted first and then experimentally discovered, unlike this thing. And the topological band theory, this is the most, you might think insulators are the most basic and boring states of matter, because electrons are bound to atoms and cannot conduct electricity. The atomic states may broaden into bands, and occupied states from the occupied states form the valence band, and the unoccupied states form the conduction band. And you can actually gradually move from an atomic insulator to a band or a covalent insulator, and they're topologically equivalent, right? The size of the band gap and all does not matter. As you're going from the atomic level to a band level, what matters is that this gap remains. And so insulators are topologically equivalent if they can be continuously deformed into each other while keeping the energy gap not fixed, while keeping the energy gap open, is what I meant. The energy gap should remain open. Just like the donut can be made into a coffee cup. The question was, are there phases which are not topologically equivalent to the trivial band insulator? And we have found phases which are not like the band insulator, but these were the quantum Hall phases. But the question was, where there were states in the gap, the question are there topological phases with unbroken time reversal invariance? And for the first answer that came up was something which was called the quantum spin Hall effect, where they just thought that you might have integer quantum Hall effect for spin up in one direction and integer quantum Hall effect for spin down in another direction. And these two, the magnetic fields in some sense cancel each other, like something that there are models of this kind. The sigma xy for the spin up and the sigma xy for the spin down can be quantized as an integer modulo 2. But spin actually is not a good quantum number in the presence of spin orbit coupling. And it was realized that even without SZ conservation, for time reversal invariant systems with half integer spins, the two classes survive. And you have some generalization of this, which actually does happen. You can no longer interpret it as independent quantum Hall for spin up and spin down states, but essentially the reason is that this is something, that time reversal symmetry changes B to minus B, and spin up electrons go to spin down electrons. So, but there's something called Kramer's theorem, which says that for a time reversal invariant system for spin half particles, the time reversal operator is anti-unitary. And this is something you've already discussed, I guess. So all time reversal invariant states have to be doubly degenerate, because if they were the same state, if I assume that under time reversal t of psi goes to just some phase times psi, then what happens is if I take t squared of psi, then t squared will be equal to 1. And it will contradict the statement that t squared is equal to minus 1. So under time reversal, when it acts on a state, you have to go to another state, which is not just a phase times the same state, because it cannot be the phase time, the same state. So all time reversal invariant states have to be doubly degenerate. So essentially what it means that if you have energy bands, then at the two time reversal invariant points, which are k is equal to 0 and k is equal to pi in a one-dimensional system, or k is equal to 0 and k is equal to pi by a, you have to have these, the states always be doubly degenerate. You can have a conduction band and a valence band, but the states in the gap, if they're of the form that at these 2 points they have to be doubly degenerate, then you can connect them up only in two possible ways. Either the same state over here gets connected, these two states get connected here, or different states at these 2 points get connected. And these two are always in two different topological classes, because this will have an odd number of bands crossing the Fermi energy, where this will always have an even number. Because if I move this over here, both these states will go away. Whereas if I move this over here, this line will move up, but this line will cross the state. So there is always once I fix these two ends, then it always makes a difference whether you have an even number of crossings or an odd number of crossings. So these two are in two different topological classes. This is a generalization of what happens in one dimension, which I'll also explicitly do again, but Vijay has already done that as well. Right? So these are these two classes of models. So what are the consequences of this? We essentially expect to see edge states like in the quantum Hall problem, and two states of opposite chirality at each stage, which are time reversed partners of one another. And the experimental consequences of this that was expected is you would expect a two-terminal, because both at the top and the bottom level, you'll have one state going this way and the time reversed partner going the opposite way, and the same at the other end. So if I look at the two-terminal conductance, I'll have one state from here going this way, one state from here going this way. So what you would expect is to find something like a 2e squared over h conductance. So, but experimentally, when this was done, they realized, they found that when this thickness is very small, then the system is not a topological insulator, because you need a band inversion, which does not happen over here. But when the thickness is large enough, there is band inversion, and the system is a topological insulator. So the samples 3 and 4 where the system is large enough, D is large enough, the conductance is 2e squared by h, whereas for other samples, conductance is arbitrary. It does not have to be 2e squared by h. So they could prove that for topological, that they do get a topological insulator in this kind of a well system. And this was seen by Koenig et al. In 2008. So you get conductance quantization, which is expected of a topological insulator. This here is longitudinal conductance, because this is a two-dimensional sample, and they're looking at it's a generalization of the quantum Hall effect, right? Without magnetic fields, but you have two edge states on either side of the sample. People also found 3D topological insulators, where surface states replace the edge states as current carrying states, and the bulk states are insulating. And this is where it turns out that the electrically conducting states on the surface are Dirac cones, which are excitations that obey the Dirac equation instead of the usual Schrödinger equation. Yeah, I said you had mentioned that they should not be called Dirac cones. The material that they use is something called bismuth selenide, which is an insulator but has surface states. And by using RPIS, which shows you a picture of energy as a function of momentum explicitly, they could see these Dirac cones. One can also have topological superconductors, because as far as these kinds of models are concerned, there's not that much difference between a superconductor and an insulator. All that matters is that both of them have an insulating gap as far as symmetry and topology is concerned. So they are like insulators and can have valence bands and conduction bands. And they can have gapped bulk excitations but can have states in the gap which are like edge states. The only difference between topological insulators and superconductors is that topological superconductors have particle hole symmetry. And so the excitations are not really fermions, but they are what are called Bogly bonds. They're linear combinations of the electron and hole states. And what you can see is that whatever state you have in the conduction, the valence band and the conduction band, they kind of mirror symmetric with respect to each other. And precisely at zero energy, you don't need to have a partner. Because at all other energies, if there's something which is at a minus E, you will also have another state which is at plus E. So that's how, I mean, that's the only thing about a topological, about a superconductor. Topological superconductor was a topological insulator. And again, I'll come back to this when I discuss the Kitaev model, which I'm planning to do, 1D Kitaev model. What you find is that you can have states at zero energy, and you find that you can't move it away from zero energy because it doesn't have a partner. These states are at the edges of the system, which is again something I'll come back to. And the reason, again, topological superconductors people have been studying with so much interest is because these Majorana modes give a new way of storing and manipulating quantum information, because the two Majorana modes at the two edges form a non-local fermion, and hence it's like a single, they can store a single qubit of information non-locally. It can be hence immune for decoherence and used for topological quantum computation. And they obey non-abelian statistics, which is more exotic than fermions or bosons or even anyons, which are actually abelian. So this is what is the interest in these things. Okay, so yeah, hopefully I'll finish in another half an hour. You can also have explicit models in one dimension, which are these one-dimensional. This is what I wanted to discuss in some detail. But I mean, you have already discussed the Su-Schrieffer Heeger model in some detail, but let me just discuss it again, because it's probably just repeating what he said, which he already gave a much more basic introduction to this model, but I'll give it in a more algebraic way over here. Essentially, the Su-Schrieffer model is a model of alternating long and short bonds with periodic boundary conditions and something like with 2n atoms. It will form a two-band model, because I can write down the Hamiltonian in terms of the creation annihilation operators of these at these various sites. He was talking in terms of the Slater determinants and so on, and I'm directly using second quantized notation, which will take care of all of that. So one can directly write down something like a model like this, which is just telling you that on alternating sites, you have a hopping element T0 plus delta T. And this is like, this will hop from B to A. And with T0 minus delta T, it will hop from A to B, right? What? It can be, yeah, no, it doesn't have to be. It's just a chain. Delta T can be equal to T as well. It doesn't have to be small. I mean, I could have called it T1, T2. It's just that I'll use T0 plus delta T. I can solve this model explicitly by Fourier transforming. And what you find when you Fourier transform this model is that you can always write it as something which I'm calling as a vector D, which is a function of k dot sigma. And this vector D has components dx, which is of the form T0 plus delta T plus T0 minus delta T cos Ka. dy, the y component of t naught minus delta t sine ka, and dz is equal to 0. And as Vijay already said that you can, it's the two-band model, if there is no, if gapless at minus pi by a, this k is in units of minus pi by a. So at minus pi by a and pi by a, it's periodic, so it has to be the same. And you can, if there is a gap at this point, then this is a thing with a gap and this is a thing without a gap. And you can show that this particular Hamiltonian just has this energy dispersion. So when delta t is equal to 0, then this energy goes to 0 at Ka is equal to plus minus pi. So when delta t is equal to 0, then you get this gapless case. If delta t is non-zero, whether positive or negative, you will get these, a gapped spectrum. Okay? So looking at the spectrum, you can't say whether delta t, I mean, it's the same for delta t is positive and negative. And I'll show that delta t is positive and negative come in different topological classes. But delta t is equal to 0, you get a gapped spectrum. One can actually compute the topological invariant here by integrating the Berry connection. One can find out get the wave functions, find out the Berry potential, Berry connection explicitly, as he also mentioned over there. And you can show that for delta t, positive and negative, they are in two different classes. Okay. What? Let me come to that. I'm saying that, yeah. But I want to see these two topological phases pictorially. And the reason, the reason that one is getting dz is equal to 0 is because the atoms at A and B are the same. So that gives us, there's an extra symmetry giving rise to dz at 0. So D is constrained to lie on a plane. So I can ask the question, D is a function of K, and one can ask the question, how many times does a vector dk go around the origin as K evolves through the Brillouin zone, that is, go from minus pi by a to pi by a. If delta k t is positive, then what you can show is that I can start from this point where a is just twice delta t, because if delta t is positive, then at Ka is minus pi by a, right? You can show that dx has a, these two add together to give you twice delta t, because this is equal to minus 1. So these two will give you twice delta t, and dy will be 0. So you can explicitly work out what you get at this point, at each of these 4 points, right? You'll get twice delta t here, twice t naught here, you'll get some value here and some value here. And you can see that as you go from minus pi by a to pi by a, you're going around in this direction. Over here, if delta t is negative, you can see that you go around in this direction, but because delta t is negative, this comes to this side of the origin. So you can ask the question of how many times does the vector dk go around the origin as k evolves through the Brillouin zone. And it's 0 on this side and it's 1 on this side. And to change this, you have to go through the configuration where delta t is equal to 0. So the point is that on the left, because if we are thinking of the base space, delta t is equal to 0 is the point where the energy goes to 0. So that is a special point, right? And you want to see how many times you're going to wind around the point where the energy goes to 0. So here, since it doesn't wind at all, you can actually shrink the circle to a point, and the Berry phase turns out, you can compute the Berry phase explicitly, it will turn out to be 0. On the right, you can again, you can see that encircles it once, and because when the K goes around the Brillouin zone, so the winding number as the K goes around it once, dk goes around it once, so the winding number is 1, and there's a Berry phase of pi. So these two are in two different topological sectors with different Berry phases. Delta t is 0, and E goes to 0. As he already explained, then there is no phase for the vector goes to 0, so there is no phase for it. It's not defined. Yeah. Huh? E goes to 0. Yeah. D vector. Sorry. Yeah? dz is 0. If dz is 0, then you can take it off the plane. Then it can go in between the different topological sectors. When dz is not 0, the spectrum is gapped, I think. Let's check. Yeah, for any value of d, it will be gapped because you'll also get a dz squared over here. Yeah, and as far as the topology is concerned, you can take it off the plane. So you can go from one to the other, not by going through the origin, but by taking it off the plane. For dz not equal to 0, it doesn't have any topology. Yeah, this comes in the thing with no topological symmetry. And then we can also look explicitly for the edge states in the Su-Schrieffer Heeger model, which again is something which Vijay already did. In this case, because I've written down the model, it's simplest to see when delta t is equal to plus minus t naught. Because in those cases, if delta t is equal to t naught, then this term goes away. If delta t is equal to minus t naught, this term goes away. So you can see that if delta t is equal to plus t naught, then this is you only have the double bonds, and there are no edge states. And if delta t is equal to minus t naught, then there are two edge states at the end, which are just left out. So these edge states are again topologically protected even when delta t is not equal to plus minus t, as he said, but then they go into the bulk, meaning they will go exponentially into the bulk, but they will remain at 0 energy even though they're not completely localized at the edge. One can have a similar model also for one-dimensional topological superconductor, which is again, it's as he said, it's one more Kitaev model, which is again an extremely simple model to study. It's a toy model with Majorana mode, which is the one-dimensional spinless p-wave superconductor. So here again, what you have, I can explicitly write down the model in a 1D chain. I have a chemical potential term, I have a hopping term, and I have what is called a pairing term. The difference between these two is that here you can see that this is just, it's not of the form Cx dagger Cx. It's not of a particle number conserving term, right? It either creates two particles or destroys two particles. And one can, the way Kitaev solved this model was to rewrite it in terms of Majorana operators, and you can rewrite it in terms of this gamma ax plus I gamma bx cx, and cx dagger is half gamma ax minus I gamma bx. And once I rewrite it in this entire thing in terms of these operators, then I can easily solve it in two limits. I can assume that this mu is less than 0, and I can put t is equal to delta is equal to 0 and rewrite it in terms of Majoranas. Then this turns out to be my Hamiltonian. Then what you find is that the only thing, I've written it in terms of Majoranas, there are only these Majoranas at the same site, which are, the bonds are only between these two, the hopping. mu gamma Bx, gamma Ax. So the bonds are only between these two sides. And in this case, there is a n, does n have to be even? N I don't think has to be even here. No? No?
Each bond is a site.
Yeah, each bond is a site. Yeah. This is a site. This is site 1, site 2, site 3. In fact, here it's easier to see why a unit forms because you don't want to break a fermion. In the Su-Schrieffer model, it's harder to explain why that doesn't. On the other hand, if you, in the second limit, you can take mu is equal to 0 and t is equal to delta as non-zero. Then what you find is the Hamiltonian, the same Hamiltonian, in terms of the Majoranas, can be written in this very simple forms because you only have t and delta equal and no mu. The bonds are only between B of one side and the A of the other side. Okay. In this case, what you see is that there are two unpaired Majoranas at the two ends of the model. The Hamiltonian does not at all, if you depend on these two, it is independent of the gamma A1 and gamma Bn because they never enter the Hamiltonian at all. They have dropped out of the model. So what happens is that we can form an ordinary but non-local fermion from these two end Majoranas, which is F is half gamma 1 plus I gamma 2, F dagger is half gamma 1 minus I gamma 2. And the energy is independent of whether this fermion state is occupied or not. So what you have is a non-unique ground state, or rather the ground state here is doubly degenerate because whether you have 0 or 1, which is F dagger 0, both are ground states of the system because the Hamiltonian is independent of this state completely. So this again, this is another reason why these Majorana modes are have gotten so much interest. They form a single qubit of information non-locally. They can carry they're a non-local fermion and it's like a two-state problem which can carry a single qubit of information, and it can be immune from decoherence because if you do something at one end of the system, it will not affect the occupation or non-occupation of this particular state. It's not very hard. In fact, just doing simple algebra, one can show that these excitations, if I take these two and another two of those, one can show that you can have non-abelian statistics in such models very easily. So these can be relevant in quantum computation. Okay, so this is mainly what I wanted. What? Yeah.
They must have a condensate. There has to be some pairing. And what is spinless P-wave mean?
Spinless P-wave, you can.
There are two electrons and pair.
No, you. How do you say it?
So I think
You.
often it's induced by proximity effect.
Yeah, exactly. You put a superconductor next to one of these things and induce superconductivity in it by proximity. It means both are up, both the spins are up, right? What happens is that you put an ordinary S-wave superconductor in proximity to a topological insulator, then you can, because I'll have to draw it, you can show that, how do I say this? Okay, I may not be able to do it right now properly, but I can talk to you afterwards. What you find is that you'll get something like this, and then you can show that if you put your Fermi level somewhere over here, then this is an effectively P-wave-like superconductor. But I'll have to do it correctly and show you. But this is what is done by proximity of a S-wave superconductor with a topological insulator. Yeah.
So basically what happens, just spin off the
Yeah.
density, that is, the spin locks to the movie. So if you put the thing
Just
put it slightly above,
right, you're putting it in between these things, right? That's what I meant. You have to put it like this, such that you can put it here. And you can, from two sides. Okay. Yeah. So now let me come to the end of this thing with what are the current frontiers in the field. As I said, many new materials have been found which are topological. These are not only insulators, but what are called semi-metals, wild semi-metals, Dirac semi-metals, which are basically generalizations of graphene to 3 dimensions, which have Dirac cones which touch at the Fermi level, and where valence and conduction bands touch. One can get something which are materials which are higher order topological insulators, which basically are sometimes you can get 2D topological insulators with not edge states but with corner states, which are there only at the 4 corners. You can get 3D topological insulators which are with hinge states. You can get 2D topological superconductors with corner Majoranas. So there's an entire zoo of different kinds of states which can, materials which can be obtained. One can also get what are called Floquet topological phases, which are new topological phases and edge states which can be obtained by shining light on topologically trivial systems. So, and then you can find that these bands are characterized not only by the Chern numbers, but there are also other kinds of winding numbers which are needed to classify these topological phases. And topological phases of periodically driven systems have been characterized using Floquet theory. And then, of course, once you include interactions and topology, one knows one strongly interacting system which has topological protection, which is the fractional quantum Hall state. And one can have generalizations of them, which are the fractional Chern insulators of fractional topological insulators. And as for the quest for Majoranas, as I said, ordinary superconductors in proximity to topological materials are what give rise to this. This is again something which I was trying to draw over here, which I can explicitly draw and show. One-dimensional wires with strong spin orbit coupling and magnetic field, proximity coupled to this superconductors gives you an effective P-wave topological superconductor. And this is something I wanted to mention here, that Majorana modes seem to have been seen. At least there are some experiments which claim that they have now evidence for these things. People are also studying, trying to look for other kind of fractional Majorana fermions or parafermions. And I'm not going to talk anything about my own work, so I thought I'll just give a glimpse of my collaborators instead in the last several years, 5-6 years. Yuval Geffen and Ganpati Murthy, with whom I've been working on quantum Hall effect. The two Arijits and Soren, who are my former students and faculty members elsewhere, with whom I'm continuing some collaboration. Priyanka, who was a postdoc with me, who's now in TIFR as a postdoc. And these 5 are my former students who graduated in the last 2-3 years. And these are my current students. And these are students and postdocs of collaborators. So this is kind of the people with whom I've been working in recent times. And what we've done is we've explored various aspects of these phases, all topological phases, mainly quantum Hall effect, graphene, silicene, wild semi-metal, Floquet-induced phases, and Majorana modes. So let me end with the takeaway points that I have over here. What these are is that there is a new class of materials defined by interplay of symmetry and topology. You have insulators, superconductors, metals, which now exist in topologically trivial and topologically non-trivial classes. And even materials in topologically trivial classes can be made interesting or topological by shining light on the material. All kinds of exotic excitations exist in these materials. Relativistic particles like Dirac and Weil fermions, particles with unusual statistics like anyons and Majorana modes, and other particles like monopoles, dyons, axions, etc. And so what you can have is exotic particles at exotic effects at low energies. So with that, let me end.